Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn how to perform sentiment analysis with TensorFlow and Keras. This is a natural language processing binary classification problem, and we will train a recurrent neural network on the IMDb large movie review dataset. So here at the time of this tutorial, TensorFlow 2.0 is an alpha release. So here in our virtual environment, we'll make sure we install TensorFlow GPU 2.0 alpha, and then we're going to import TensorFlow datasets and TensorFlow. Now we're also going to import matplotlib, and here we're just going to define a function so that we can plot our accuracy and our loss and so on later. So once we have the basics set up here, we are going to set up the input pipeline. So here, first of all, we're going to use our TensorFlow datasets and call the load function from that module. And we're going to use the string IMDb underscore review subwords 8K. And the load method will understand that and pull that dataset. And here, for the as supervised parameter, we're going to set it to true, which means we want not only the features, but also the labels. And with info is we want, in addition to the features and labels, we want the information associated with this data set. And we store that in our two variables here, dataset and info. Then we're going to create a train dataset and a test dataset. So these two variables, and we're going to assign them to, so we're going to grab from our dataset, we're going to grab our train data, and then we're going to grab our test data from our dataset and store it in these two variables. So now we have our train dataset and our test dataset, and this consists of the movie reviews. So it's a sequence of words, so just a movie review, and then an associated sentiment or classification, whether it's good or bad, a good review or a bad review. So that's our data. We have train and test datasets. So for our recurrent neural network, it doesn't actually take in just words, raw words by themselves. We need to convert them to a mathematical representation that a network can understand and do backpropagation, gradient descent, and learn from it from a mathematical perspective. So we're going to create a tokenizer. And here, so a tokenizer basically grabs our sequence of words and splits it into individual units of words. And here we also want to encode those words. So we want to convert those English words into a numerical representation. So here we're going to grab our info that we loaded here from our data set. We're going to grab the features and the text in particular, the text features, and then just get the encoder from it. So that's how, and then we store that in a tokenizer variable. For tokenize, this object here is going to tokenize and encode our text data. So let's go ahead and print our vocabulary size. So that's the number of unique words in our data set, and that's contained in our tokenizer object. So we call vocab size from our tokenizer. And how does it know? Well, it's because we actually grab the features from the info. So we're still dealing with our dataset info, text features, and encoder. So it's inside this object, that information. So that's how we get the vocabulary size printed. And we have 8,185 words for our vocabulary for this dataset of movie reviews. So now let's go ahead and do a simple test here. So we're going to create a sample string variable, and we're going to assign it to TensorFlow is cool. So now we're going to create a tokenized string variable, and we're going to assign it to our tokenizer object and .encode. So we're going to call the encode method on our tokenizer object and pass in our sample string. So we're going to grab a raw string and convert it into a mathematical representation, as you can see here. So and we print it out. So our tokenized string is this. So we split words and convert those words into numerical values. And now we can also get our original string here by calling the decode method from our tokenizer object and pass the actual tokenized string, and that's how we can convert back. And you see and we print that out. So as we can see, the original string is TensorFlow is cool. And then here we just do a simple assertion to make sure that the strings match the original and the sample, and they do. So now, so this TensorFlow is cool seems like 3 words. So why did we get more than 3 elements here in our list of tokens, of encoded tokens? Well, it's because if the word if the tokenizer encodes a string by breaking it into subwords, so if the word is not in its dictionary, that's what it's going to do. It's going to break up the word into subwords, and that's why. So we have TensorFlow is cool, and then the period counts as well as a token. So that's why, because our word wasn't in our vocabulary, here our function did quote unquote the best it could here to split it. So that's why we get this behavior. And here simply we do a for loop. So for each one in the tokenized string, for each tokenized string, TS in tokenized string. So for each token, we just print it, and we call decode on each one, of course, here. So we also get the second part. So just TS for the first, and then tokenizer decode, and we see the equivalent, what it actually is, the conversion. So we start with our data set, which is just strings, text, movie reviews, and we tokenize and encode them. Great. So now we go to the next step here. So we're going to actually shuffle our trained data set. So we have our trained data set here that we created from our data set. And we're going to call shuffle. And so we're going to shuffle and randomize the data. And we're going to pass in for its parameter buffer size 10,000, which means we're just going to shuffle and sample from 10,000 here. So that's our trained data set. And now we also want to convert it. So we want to call padded batch on the trained data set. And the reason is because for these reviews, the reviews vary in length. So they have different number of words and so on, but we want a consistent shape. So if we want a consistent shape for our sequences, we want to pad them based on the largest one, the largest shape, the largest shape for the largest sequence. So padding means we just fill it with zeros in this case. So the default parameter for that is 0. So we don't set that. That's the default. That's one of the default parameters. So it's suppose from our trained data set output shapes the largest. I don't know, for a given dimension. Let's say it's 10, and we have one here. Here a sample that is 4. And then for the other 6 elements, they're just going to have a 0. It's going to be filled with zeros. So that's what we call. And we're going to do that for each element in the batch. That's what we call a padded batch. So we have this consistent shape. And of course, we pass the batch size, which we arbitrarily picked as 64 as one of our hyperparameters. And we do the same thing for our test data set here. So we have our test data set and the same thing, padded batch, and we just do the same thing except with the test data set. And here for the test data set output shapes, it just grabs the largest one, and we do the padding based on that. Okay, so once we have our padded batches, we're ready to create our model. So we're going to use tf.keras.sequential. So we're going to create a basic sequential model here with Keras. And for the first layer, as this is standard when creating recurrent neural networks or LSTM specifically, we want an embedding layer here. So the first layer in the sequential model is an embeddings layer, and this just takes in the vocabulary size. So from our tokenizer, we can grab the vocabulary size, and then in the second parameter 64 is the output shape for the embedding layer. So all this does, this embeddings layer, is for a given input, it just converts it to a specified size. So we also have a consistent output shape output for the embedding layer, no matter what is the input. So here within the layer, within the model itself. So we have our embedding layer, and then for the next in this sequential model, we have for the next layer we have an LSTM layer, so tf.keras.layers.lstm, long short-term memory cell, and that encapsulates both the long-term and the short-term memory of our network to learn long-range dependencies. Now, usually this only does it going back, so it looks at past elements in our network, in our sequences, but and here we have 64 is just the shape. So how many neurons in this LSTM cell here? But we're going to actually wrap the LSTM layer into a bidirectional layer. So tf.keras.layers.bidirectional, and what this does is it still learns long-term dependencies, long-range dependencies going backwards, but because it's bidirectional, wrapper, we also learn dependencies going forward. So given so for a given word, for example, we don't just want to learn features so words from that came before that word, but also the ones that are after. So we go backwards and forwards in the sequences and learn the patterns, the features going both forwards and backwards. So very nice. We're just wrapping our LSTM layer in a bidirectional layer. And now we have the next layer is a TF.Keras layers dense, so a dense layer, or what we would think of as a fully connected layer, so a dense layer with 64 neurons. So, and here's just like a flattened layer essentially here, 64. And then for the activation function for this dense layer, we're going to choose ReLU, very standard. And for the last layer, remember, we're doing binary classification. So we're classifying movie reviews as either positive or negative. So since we're only doing binary classification, here for our dense layer, we're only outputting one. We just want one output. It's either good or bad, and or positive or negative. And then for the activation function, we want a sigmoid. It's just binary classification. So we don't really need softmax at this point. So sigmoid will be good. So that's our sequential model, our recurrent neural network with LSTM cells and a bidirectional wrappers around them. So very nice and very simple to create with TensorFlow and Keras. So now we're going to compile the model, so model.compile, and we're going to specify 3 parameters. So we have the loss parameter here, and for the loss, we're just doing binary cross entropy. And optimizer, we're doing atom, again, pretty standard. Atom is usually the choice that you want to go with. And metrics, we're just tracking the accuracy. That's the only metric really that we care about. So for our metrics list parameter, we only specify the accuracy. So we compile our model. So now it's time to train the model. So we're going to create a variable called history. So we store the output, the history essentially of the training, and we're going to grab our model instance and then call the fit method on it. And we're going to pass in these parameters, so our trained data set that we created earlier, and then our epochs. So we're going to keep it simple, just do 10 epochs here. And then for the validation data parameter, we passed our test data set, which we're going to use as validation. And as you can see, for every epoch, we print out the stats here. So the accuracy, you can see it increases gradually, and then it drops. But I mean, this really depends on the variance in the data and so on. So it doesn't have to just increase. It can actually do some have some variation. That function, the loss function, the accuracy can have some variation, but over time and over many epochs, it should converge to a local minimum of the loss function. So here we're now, after we have a trained model, we're going to call the evaluate method on our model instance. So we're going to pass in our test data set, and we're going to just print in our test loss, our test accuracy. So we're going to print those out. We have our accuracy around 80%. I mean, it's not bad. And then the loss is just 0.5533. So now so this model does not mask the padding applied to the sequences. So of course, this can lead to a skewed model if we train on padded sequences and then test on unpadded sequences. So that padding that we added, we also have to take that into account, because that can also affect our prediction. So ideally, we want the model to ignore the padding. But so here we just basically create a function here that adds padding. So given a size, so we pad that along. That's how much we pad based on that size. So we just create that simple function there, and then we're going to create also a function that is sample predict. So it's going to just grab some sample text and then a Boolean parameter here, whether we want padding or not. And feel free to pause here and just see how this works. Basically, we're just testing with and without padding our trained model. So here we have a sample text here, sample pred text. The movie was cool. The animation, the graphics were out of this world. I would recommend this movie. So as you can see, very positive. This is a positive review. You can see it has words like the movie was cool. The animations and the graphics were out of this world. I would recommend this movie. So the model has learned that some of these words correlate to a positive review, and other words correlate to a negative review. So let's go ahead and call our sample predict here, which contains our model predict call here. And so here we call actually tf.expand dimensions on this tokenized sample prediction text, because we want to add a batch size dimension here at 0 at the index 0. Remember, because we also need a batch dimension here for our model. So here we call sample predict, we pass our text, and then we say, so here without padding. So we specify padding equals false, so we're not going to do this part, so without padding, and we're going to print the predictions here. So 0.689. So if it's above 0.5, we consider that a positive review, and if it's below 0.5, we classify that, we consider that as a negative review. So the model thinks this is a positive review, which is correct. That's what we would expect. This trained model has learned the patterns for the positive words. And here, we're going to do it now with padding. So setting padding to true. And as you can see, it doesn't change that much in this particular example, but it changes a little bit. But it's still classified as positive because it's learned those patterns. And now here we can call our plot graphs function that we defined earlier and pass in our history, which was the output of our model. As you can see our history of our trained model, its history, and then the accuracy. That's the metric that we care about. So we have that. So we have epochs versus accuracy. And here you can see just as a function of epochs how the accuracy changes. And this can have a lot of variation. Actually, training a recurrent neural network can take a long time. But for this simple example, we can just see just how the training evolves over time. And we still get some very decent accuracy for this binary classification problem for sentiment analysis of movie reviews. And here we also see the loss. We plot the accuracy, and we also plot the loss function. So the training loss decreases as we would expect. The validation loss is a little more strange what it does, but just gives you a general idea of what's going on with this recurrent neural network. So now we can we did only for a recurrent neural network, we only had one LSTM layer, but of course you can add more. Yes, that adds more learnable parameters to our network. It's going to take longer to train, but we have that option. If you think your model is underfitting and you want to add more parameters, more layers, you can do that. You can do some analysis about that. But suppose we want to stack 2 or more LSTM layers. So here, it's basically the same as before. The only difference here is we change our LSTM layer, wrapped in a bidirectional layer, to 32 neurons instead of 64. And then before that, after the first embedding layer, we're going to add another LSTM layer here, long short-term memory cell, wrapped in a bidirectional layer, so we can learn forward and backward long-range dependencies. And we want to specify this parameter return sequences as true. So the default value is false, but we want to set it to true in this case. So it's going to return the full sequences of successive outputs for each time step. In this case, it's a 3D tensor of shape, batch size, time steps, and output features. Otherwise, if you leave the default parameter as false, it only returns the last output for each input sequence, which is a 2D tensor, right? So here we're learning more features. Essentially, we're getting more learnable parameters with adding this layer here, which we think will probably increase the accuracy and yield a better model. So let's take a look. So let's go ahead and compile this model. Model.compile. Loss still binary cross entropy. Optimizer, gradient descent optimizer is still Atom, and our metrics is the accuracy. And so we call model.fit. Same thing. Train data set. 10 epochs validation data parameter is a test data set, and we have our history. And as you can see, so now the accuracy, see, it steadily goes up, and it didn't tend to drop in this case. It just went up to 96% accuracy, which is really good. And the validation accuracy 80%. So we can just go ahead and print that. So we have the loss and the accuracy here. And now we're going to test this on a negative review. So the movie was not good. The animation and the graphics were terrible. I would not recommend this movie. So the network has learned that these words correlate to a negative review. So this is what the network is doing, really. It's learning this function that is mapping, is trying to find the function that best maps these inputs, the reviews, to the outputs, which are the sentiment, essentially, whether it's a positive sentiment or a negative sentiment for this review. So we call the sample predict function as before, same thing with no padding. padding equals false, we see the prediction. So this is below 0.5, definitely. So this is a very negative review according to the model, which it is. And now we do it with padding, and it's relatively significant, the change, but it's still definitely a negative review. So there's a change with and without padding, but still the model classifies correctly, as in this case as a negative review. So we can go ahead and plot that. So as you can see, both the train and validation accuracy increase and they sort of stabilize. And then we can plot the loss. So the validation is a little not as consistent, but the training loss consistently keeps going down. But again, in this simple example, just to give you an idea of what's going on with this model. So that's it. So sentiment analysis NLP problem with TensorFlow and Keras. So thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.